If you run a while loop like this in a language like C or Java, then it'll just run forever. It won't give you a value, but it won't actually run out of memory or anything bad like that either. If you write a program like this in a language like C or Java, where you have a function f that's supposed to return an integer and the body returns the result of f, then most likely this is not going to be an infinite loop. It's eventually going to run out of memory. And this has to do with the different way that languages like C and Java treat recursive calls versus loops. What's going to happen with curly? This is the same sort of example. We've got a function f, and then we encode the recursive function f by having it take itself, and then it's just going to call itself passing itself. And then we started off by calling f with f. So you see f applied to f is going to turn into f applied to f, which turns into f applied to f, and so on. The question is, will this eventually run out of memory, or will it just run forever without using more memory than it starts with? We can answer this question by stepping through the interpreter. So let's imagine that we're interpreting this expression in curly, and let's just do it in rewriting right now instead of going through the interp function. So if we do a rewriting reduction, then that means f equals this lambda f, so we replace that lambda in each of these uses of f, and we end up with this expression. So this first copy here, that's this f here. The second copy here is that second f. Now this expression looks a little funny, but we can just apply our rules of function calls, which is that this second lambda here is going in for f in the body of the function f. That is, when we do that substitution, we get right back where we were. Right? This lambda went in for this first f right here, and the same lambda went in for the second f right here. And since we just took that step, we know that the same expression is going to end up stepping again to the same pattern. So no matter how long we try to reduce this, as long as we only write the current expression on our piece of paper, we never run out of paper. The expression does not run out of memory in that sense. Let's try that from the interp view. So I've skipped the let step and just expanded it right out to a lambda. And as usual, I'm drawing a box around things to say parse of this concrete syntax. So what happens when we interp the parse of this lambda applied to itself? Starting with the empty environment and the empty continuation. This is going to be a lot longer than the rewriting view, but I think you'll see we get to the same conclusion. So first, interp of an app form starts interpreting the function position, and it builds an app rk to remember the argument expression. Happens that these two expressions are the same, but this expression that we're interpreting is the function position right here, and this expression that we're remembering in app rk is the argument expression here. And of course, we keep the current environment even as we use the current environment to interpret the function expression. So what does interp do when it sees a lambda? It's done quickly. It just creates a closure. So that's the closure that it creates there. You see this closure corresponds to this lambda. It has an argument named f, and it's got a body which is f applied to f, and it's in the current environment, which is the empty environment. Once we have gotten that closure value, then we're ready to continue with the current continuation, which is this app rk that I copied right down here. So when we continue with that app rk, you can go back and look at continue app rk, but what it does is it starts evaluating the argument expression. So we'll have an interp with the argument expression, and it takes this closed v and puts it inside of a do app k, which means once you get a value for the argument expression, now you can actually apply this function. And the rest of the continuation after that is done k, so that's why we have done k down here. Once again, we are interpreting a lambda expression, so once again, we'll continue right away with the closure. Here, this closure corresponds to this lambda, which has argument f and body f applied to f in the current environment, empty environment. And then we continue with the rest of the continuation, which is this do app k. Do app k then, in the continue case, says we've got a function and we've got an argument, start interpreting the body. So we will interpret the body expression ff. As we interp, we bind this value, this closure here, to f in the environment. So we see that closure bound to f, extending the environment, and this empty that we extend, that is the environment of the function that we're calling. And once we get a value back from that application, then we continue with the rest of the continuation, which is just done k. So that's why we have done k here. Okay, what does interp do? Well, it starts evaluating the function expression, remembering the argument expression. We're going to keep writing this environment, so let's give it a short name, e1. That means that we are currently interpreting f applied to f in e1, and now interp is going to start evaluating the function expression for the current environment, remembering the argument expression, right, that's this f, in the current environment. I know it's taking a while, but we're getting to the punchline. What happens when the interpreter encounters a variable? It looks it up in the environment. In the environment E1, it finds this closure. Right? So we skip showing lookup since we're just showing interp and continue, but it gets a value right away. And since you get a value right away from the environment, you can continue with the current continuation, which is this app rk. App rk, as we've seen, starts evaluating the argument expression in its environment. It extends the rest of the continuation done k with the do app k to remember the value for the function. And now we're interpreting f in E1 again, so we continue right away again with that closure that we find in E1. We continue with that closure value and the current continuation, which is this do app k, and that means that we will start interpreting the body expression in the extended environment. And if you extend empty env with f mapped to this value, you get to the same E1 that we had before. So here, now you see we've gotten to the same place that we were before. An interp of f applied to f in E1 and done k. That means that in our interpreter that we've implemented in Plait, it's acting just like the rewriting version. It's going to run forever. The expressions don't get too big, and so we won't run out of memory.